We are looking at 7.2 today, and 7.2 kind of makes that connection back to 7 or 6.1 with Riemann sums. So what we're doing is we're now integrating area between two curves. So with Riemann sums, what we did was integrate the area under the curve from the curve to the x-axis. It was auto-bounded by the x-axis. What we're doing now is saying, okay, instead of making the lower bound the x-axis, what if we make the lower bound another curve? So what we can do is we can manipulate this rectangle to find an area between two curves as opposed to between the curve and the x-axis. So what I want you to do is look at that image and draw a rectangle to represent the area of a rectangular strip between those two curves. So you can draw it anywhere you want.
I'm confused.
I want you to draw me a rectangle somewhere between these two curves. Like instead of having the rectangle between the curve and the x-axis, draw it between these two curves.
So like L sum or L ram.
So here's an example of one rectangle. You could have your rectangle there. Somebody else might have a rectangle here. So all our rectangles can be in varying locations. What is true of every rectangle I just drew?
Vertical.
They're all vertical. And they all have the same width, right? I drew them all with the same width because I used the same marker. So they all have the same width, and their height would be top function minus bottom function, right? So the top function would be here for all of them. What is that top function? Yeah. So like f of c, we'll call it. So we'll say that all the rectangles were drawn at c. So pick your rectangle and label the x value between a and b as c. So let's say I'm working off the yellow rectangle. That would make the height of the yellow rectangle, or this point here, f of c. That would mean the base of the rectangle is at what point? G of c. So the height of the rectangle would then be what? The width of the rectangle, we always just call width what? Yeah, it's the width of the pen, but we always in calc we refer to width as what?
No, yes, I had a pen. Mine ran out of ink.
Oh, you need a pen.
It's like it just stopped writing about halfway through that.
Oh.
You want what's left of the paper?
Can I draw with it?
Yes. I don't know why it always freezes.
Wait, I have a second ink cartridge, never mind.
You're good?
Yep, found an ink cartridge.
Okay, I was coming back to find you a pen.
Thank you. Ink cartridge rights, we're good.
Did you put these
We have
Okay.
ink cartridge.
Probably at some point. I mean, I eat the entire apple time. Don't eat cyanide.
All right.
Hold on. Cyanide happiness.
Would the height of the width, would the height and the width of the rectangle be different if you drew it in a different place?
Yes.
Yeah. Yes. With no height, yes.
Yes. Oh,
No.
you're saying height is,
Oh.
okay, I get you, no.
Am I right? I said no.
So it's no, you're not wrong thinking the height will be a different value, but the formula will be the same.
Yeah.
Like my C is a generic C anywhere. So like, somewhat.
Oh, bull.
Where's my wife?
Bad question.
Better call Saul.
Bad answers.
Wednesday mornings leave the bad answers.
It's Wednesday.
Tuesday afternoon.
Oh crap. It's Tuesday.
Wait, it's
We
Tuesday?
did.
No, it's I was just saying.
Me too. Like
It's
smoke.
only Tuesday.
Alright.
I thought.
How do I find the area then between the curves? What is area? Area is,
Length
Length
times
times
width.
yeah, length times width. So the area is approximately the sum of all these rectangles. So how do we write something as a sum of rectangles?
You have future choices.
We do have a couple choices, but
E is everywhere.
E for summation.
Wait, that's what E's for? Oh, that.
That's
Oh, I thought you meant like E to the end. I was like, wait.
No,
So
that
it
is-
would be E of f of c minus g of c. Times with delta x.
It's like 2 points
Oh
something.
crap.
Like 2.1.
Okay, how could I rewrite this so that it represents the actual areas under the curve?
You would mean the integral of
Yeah.
f of c from your first point to where we want to end, and then you do that minus of a b,
A to B.
maybe, and then minus the integral of g of c. Okay.
Nope. No, remember, you don't even have to make it. Sorry, those should be, and so you said C's and I wrote them, but they should be X's. Because you're doing all the X values. Or you'd have to make this deltas.
Oh, okay.
The X. We typically write it like that. But,
Well, I understood.
yeah, do you know what I'm saying? Like, C would be fine, you just have to write DC. And you can actually write it as one integral or two. So I know you read it off to me as two, which is fine. You could write it as two. Or you can write it as one. We typically will write it as one because it'll be easier to combine like terms. So like let's say this was x squared minus x, and this was x cubed minus x squared. Then you could kind of cancel out your x squareds or group them together, and you only have to plug into an x squared once instead of twice. Okay? Good?
Yeah, what about the last one?
It's the same thing. If you let the numbers of the rectangles approach infinity, it would just have the limit of the sum, which is the integral. Yeah. So like you just put the limit in front of that.
That's okay, we don't have any.
That's why I didn't write it. Okay, so you can consider the following graphs, and we have f of x and g of x on each one. They're continuous for each graph between 1 and 3, but what you're seeing is how the areas are different. So the first graph is the area between the two curves. That purple area is the area between f and g. That's represented by the integral from 1 to 3 of f of x minus g of x dx. The first one is just the area under f. So it's imagining that g is not there. So you see how the area under f would include the green space below the curve. If you did the area under g, it would be this blue space here, which we're trying to eliminate to get the area between the two. So that's how f of x minus g of x works to give you the area between the two of them. That's just kind of like where it came from. Good? Or what you would get if you integrated them separately. This minus that to give you that. Okay? So the area of a region between two curves. If f and g are continuous on a and b, and g is always less than f. G is always less than f. Why is that important? What happens if g would be bigger than f?
Then you'd be like subtracting a big.
It would be g minus f, not f minus g,
Yeah.
right?
Yeah.
Okay, for all x and ab, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a to x equal b is what?
You can go A to B, G, backslash, D.
Flip your f and g's. Remember, f is always bigger than g. So you have to subtract g from f.
Didn't we do that in the front already?
Yeah, this is like the formal definition.
Oh.
Well, this is to discuss that point that we just brought up, which is what happens if G is not smaller than F always.
Everything breaks. Space
Okay.
is an illusion.
So example number 1, find the area of the region bounded by the graphs x squared plus x and negative x, 0 and 1. So take a minute, plot those points, and get the graphs. I want you to try graphing this on your own. So graph me the x squared plus 2, the negative x.
What are you doing? Oh my God.
Good? Okay, so what are we integrating from? Good, because they gave you the bounds. Ooh.
That
What's our top function?
X squared plus
Minus the bottom function. So clean it up. You have x squared plus 2 minus a minus, so that's a positive. So now we're integrating from 0 to 1, x squared plus x plus 2. And now it's just a basic power rule problem. So you have 1/3 plus a half plus 2. So create yourself some common denominator. Good.
easy.
Not terrible. Okay. Find the area of the shaded region analytically. So we have y equals 1/2 secant squared t. What do you notice about this graph? Yeah, it's symmetric, right? So if you cut this graph in half, this area here would fold on top of that area there. What bound do we love to integrate with? 0, because it typically,
Zero's up.
yeah. Now it doesn't zero out necessarily with a sine or a cosine type function. However, it'll still be easier to integrate at a 0 than it would be at a -5/3. You gotta think a little harder about -5/3 than you do 0. So if it's symmetric, and I find the area from 0 to pi thirds, what could I do to incorporate this area here?
How about this?
Just double my answer, right? So let's integrate by multiplying by a constant of 2. So instead of integrating from negative pi thirds to pi thirds, we're going to integrate from 0 to pi thirds and double my answer. Look how smart you are. What's the top function?
One half second squared.
What's the bottom function?
Negative cosine.
Here's why you can write them as 1 or as 2. If I write this as 1, that half is kind of gross sitting out in front. If I rewrite this as 2 integrals, that half goes away, right? Because a half times a 2 is a 1. So think of this as 2 separate integrals. Think of it as the integral from 0 to pi thirds of secant squared t, because the half and the 2 cancel. What do you know about a minus a minus? And what could I do to that 4 and the 2? Yep. Out in front of sine squared t dt. Antiderivative of secant squared. How about sine squared? Okay, so if you rewrite it as 1 plus cosine squared, we still have a cosine squared. Okay, so if we do u, you have u equals sine, so the derivative of u would be, yeah, so that doesn't help me. So, any other thoughts? What could I do that I could have changed? And I know I made you write it as 2, but could we have done to figure out something for sine?
Isn't that cosine of 2t or something like that? Because I know, like, I don't know, I saw it.
Yeah, there is a double angle identity. Could also have created a common denominator before we integrated, because secant squared's over cosine squared. And then kind of combined them that way by putting this over cosine squared. They shouldn't give you a sine squared on the AP test, so I'm going to tell you to use your calculator on it, because it's a BC topic, but there are like ways to get around it, but you can use your calculator for this. What? I don't know why your text, like that's from our textbook, like I don't know why the way the textbook has you do it, which is gross, and you could do it, is to rewrite it so that you have a common denominator. So go back and like look at the
One over side.
What?
No, secant's 1 over side.
Right, secant's whatever cosine squared. So then what you would
The
do,
common denominator, you do sine squared cosine over cosine.
Yes, because what it would do, think about it, it would put a cosine squared here, which makes your u sub.
Which would allow you to just do the derivative of the integral of tangent, which is. Because the integral of tangent doesn't exist. Right? We didn't learn that.
Right.
Because I talked, so then we're just stuck again.
Tangent isn't continuous.
And book
What?
sucks.
Tangent isn't continuous, is it?
No,
So then it can't be integrated.
Yeah, so we're stuck again.
it can be on
Well, it
an
can't on a
interval.
round,
So like, we can integrate
but it can't be
tangent,
integrated indefinitely.
correct, but this is a definite integral.
Which means it's broken. Broken I don't know how to unbroken the tangent. Unless you were to do sine cosine, and then just integrate sine, and then do the one rule where you take sine over cosine. I really want to break it.
So, I'm gonna do that.
I'm glad I didn't lose a pen today.
Why? We're not gonna, you're just doing it on your calculator.
What I wrote,
What?
but like I wrote.
It's okay, what you wrote isn't wrong.
I want a piece of paper.
I just was running out of room.
What answer?
I want to discover things. I need
not
a piece
wrong.
of paper.
It's fascinating.
Okay, so use your calculator, go ahead and do the integral from 0 to 5/3 of sine squared to get this into a number.
I've always thought that this black rubber thing is not.
Wait, what was it there? What do we do?
Use your calculator to integrate from 0 to 5/3 sine squared t.
Oh, I pressed the wrong button again.
I think I'm trying to go second quiet, and then I hit my hitting clear instead. I hit clear one more time. Look at that. Oh no, the final one goes.
Why?
That's cool.
So I could have just plugged in the original.
No, because I want you to know what tangent of 5/3 and tangent of 0 are.
How do you do sine squared?
Yeah.
Sine, parentheses, like sine
Yeah.
in parentheses, so sine of x in parentheses,
Oh,
and then
okay.
square on the outside. Remember, sine squared, because we had to do that for a chain rule and trig, sine squared is really sine times sine, or sine square on the outside.
I don't think.
So what do we get for our decimal for the value?
Oh.
Probably a nice number.
I got 0.30709.
Not nice.
I got 4.1 after
Oh, I didn't multiply that by 8.
Did you multiply by 8 already, Case?
Yeah.
Well, then I
I
got
got
2.456.
Wait, we're in degree 2. No, not.
Oh,
degree.
I did
not.
it. I added
not.
tangent too.
I'm not.
Oh.
I'm not in degree.
I got 2.4.
Okay,
I
well,
got
before you add your
2.456.
tangent, what is the tangent of 5/3? I want you.
2.45. Wait.
No, I want to know what it is on the real unit circle.
Tangent of pi thirds. Pi thirds.
That's-
Square root of 3 over 2 over 2, so just be square root of 3.
Perfect. It's the tangent of 0.
Tangent of 0 is on. Oh,
It's
0.
1. Dang it.
Because it's either 0 over 1 or 1 over 0.
Yeah, I know. I did 1
Zero.
over
0 over
9.
1.
No, it's still 7.
And then you have your 8 times and the number that Noah read to me. which is
2.456.
Well, that.
No, that's
In the
multiplied by
parentheses,
8.
0.30709.
Yeah.
That?
Yeah.
Yeah. Well, there's more, but I.
That's okay, you only need 3. Okay, so you get root 3 plus that 8 number, so root 3 is somewhere around 1.7, so it's like 4.
Yeah, that's what I had.
4.188790205. No. That's
The actual is 4 pi divided by 3.
Go for some Jimmy John.
You say that every day.
I didn't get much.
He likes Jimmy John.
Yeah, we had a game.
been-
Hold
Oh,
on.
you like
Hey.
Jimmy?
Okay. Okay.
I'm down, Casey. You know, just say Miss Finn likes Jimmy Jones. You don't have to go.
Okay, if you want, you can start to sketch the graph on the next page.
Okay, one. Wow.
Well, you do want.
Oh.
Okay, so find the area of the region y equals x squared and x plus y equals 2. So x squared goes through 0, 0, 1, 1, negative 1, 1, and 2, 4.
Can't do that.
I know. So it probably tells you something about the graph, the other line. Okay, so what could we do to the other one to graph it the way we like to graph? Okay, so y-intercept of 2, slope of negative 1.
Oh, look at that. You intersect the point. That's fancy.
It does. So what we want to do is we're going to find the area of the region between those two curves, and what we're going to do is say that it is also bounded by the y-axis.
So draw a
It's almost a triangle.
But then just
So that creates a bound here as well.
draw a diagonal.
So we're finding the area in this little region here. So what would my integral look like?
From 0 to 1.
2 minus x
2 minus x minus x squared.
Pops was next.
Let me finish
Yeah.
the next two examples.
No.
Yes.
Deal.
Okay, so you have the integral from 0 to 1 of 2 minus x squared
You should all
dx. So what I want you to do is anti-derive that.
The communist leader.
Socialism is the end. I'll anti-derive.
Plug in your bounds.
that turn into? Constant.
Just like communism, we work with the promise of getting something better.
It never comes.
And then the leader takes it all.
There's a gas leak. Yeah, that's my joke. Oh wait, you say that one? Yeah. Okay. That's actually going to keep it.
That's funny.
He said I got better jokes than you. You can have that crap back. Who said that?
Yeah, my wife.
You also
Oh,
play
you win a
with
rap battle.
Texas period.
I do.
You do?
Okay. The next one we're going to do on the calculator, before we do the calculator, go to the sine cosine one. What does the graph of sine go through or start at?
1. Or 0, 1.
Isn't
0, 0. isn't it?
0, 0.
Guys, come on.
Oh yeah, cosine 0.
Those are making me sad.
Because all graph trig functions.
Okay, so then it also goes through pi 0. And it also goes through 2 pi 0.
Fascinating.
Sine goes up, so at pi halves it's at 1. And at 3 pi halves it's at negative 1.
Yeah.
Oh,
So there's sine.
oh, my first one was terrible. My second one was good.
Cosine starts at 0, 1, goes through 0 pi halves, goes down to pi negative 1, back through 3 pi halves, and then back to 1. So if you had to represent the area between these two curves from 0 to pi, what would you have to do for the first region?
The blue one is cosine.
Yes.
For the first one.
Yep, the first region or first area of the gray. So
This is disgusting.
0 to cosine minus sine. What would the upper bound be? Where do they intersect?
P by 4s.
Yes. How do we know that?
Because that's 45 degrees and they're both the same
Yep.
circle value.
So much happiness came from that.
So were popsicle sticks.
Stop. Go. Okay, why wait? Are you okay? Let's find the next region.
I'm glad I can color colors.
There are colored pencils sitting back there if you'd like to use them.
Yeah, the right next to the pop is yours, guys. She's just tempting you.
I know. Let's make this from any references to the back of the room you
Okay, so what would this region look like?
Whoa.
Onwards to
Wrong month.
can.
February's over.
Where would they intersect again? You know it's got to be between
3 pi.
pi and 3 pi halves, so that would be
7 pi.
5 pi
7
fourths?
pi. 5 pi.
5 would be in quadrant 3, guys. 5.
Okay.
And think about this, okay, right? This is pi. This is 3 pi halves. So 7 pi fourths would be much closer to 2.
Don't ask me.
But it would. Well, 8 pi fourths is 2. So 7 pi fourths has to be between these two. So 5 pi fourths, like if you don't, you know what I mean? If you can't see it that way, think about just fractions in general.
I just went up a pi 4. I found the midpoint.
Yeah, you found here, like in the middle. I almost forgot where I was going for a second.
3 pi fourths. Make me sound better.
What's the top one?
Sine.
Minus.
Sine. Sine minus sine.
Wait, so why is it 5 pi fourths?
So go to the unit circle, right? Now, we know that the cosines and sines have the same values at all the pi fourths. But they only have the same signs here and here.
Oh, that's why, because.
So they're both going to be negative and at the same square root of 2 over 2 in quadrant 3. So quadrant 3 is 5 pi fourths.
I'd just like to say my graph looks so beautiful. I'm proud of it.
Trig functions are pretty to graph. All right, and third and final region. Where are we ending?
2 pi.
Where are we starting?
5 pi fourths.
What's the top?
2 pi. Wow, I just killed that.
Graph.
What's the top equation?
Cosine.
Minus sine. I'll spare you finding all of those because that's a lot of trig to plug in.
I equals
Yes, you are. Okay.
me color
All right.
pens.
Colorful pens. So that is all we're going to look at for today. You do have some homework in the book. The way life is.
We have a track.
Look how baseball game.
You have an entire class period to do it.
Nuh-uh.
Life can be different.
I can't control that you owe me a test.
Look how beautiful.